Okay, good evening. Welcome to lecture 1.2 of Unit 2, Radiation Types. Here are your learning intentions and success criteria. Please pause the video and attempt to complete the knowledge and skills table. Okay, now hopefully going through this, we can see here we've got a lot of knowledge verbs here. There isn't much in the skills column here, but we need to know, well, what are the four types of radiation before we can define them. We need to be able to talk about the properties of these radiations. We need to know what these properties actually are. And finally, we need to know how do they radiation damage humans in order to answer this explain verb. Okay, so in our simulation that we did in class, you saw three different types of radiation. You saw alpha, beta, and gamma. And we're going to add one more to this list, beta positive. Now, the beta that you saw in class is actually called beta negative or beta minus. So we've got four types of radiation we need to worry about for this unit. There are some more, but we don't really need to worry about them. Now, as we go through this and looking at types of radiation, you may want to take notes in the form of a table, because there are several things about each type of radiation you need to memorize. How you prefer to do it is entirely up to you, but a table might summarize things up. We're going to look at four radiation. They are alpha, beta negative, beta positive, and gamma radiation. And they've all got different properties for things like penetration ability, charge, mass, the ability to ionize an atom. So those are the four properties we're going to need to know. And on top of that, we should also take note of two things: the AZE notation, how do we write it, and their ability to damage us. Okay. So let's start with these four properties first. So what are these properties? Two of them are straightforward. The first is mass, and that's just how big the particle actually is. And even though we're talking about subatomic particles here, they do have different masses. Charge is whether or not something has a positive or a negative charge and how much of it actually is. You might want to look up your mass in terms of atomic mass units as well with writing these down, because otherwise you're going to just have some very, very small numbers. Now, charge is a fundamental property of all particles. We'll revisit it later when we discuss the standard model, and then electrostatics in next year's course. Now, each particle will have a charge property to memorize. Penetrating power refers to how far radiation will enter a material. We could be thinking about shielding here, or we could be talking about us, because that's fairly important. Especially when we think about the danger of radiation. Now, some radiation will only penetrate a very small distance because it gives off its kinetic energy very quickly through lots of collisions. Some radiation, however, does not and penetrates very easily. So whenever we talk about penetration, that's what you need to explain in terms of how quickly it gives off its kinetic energy. And then finally, ionization is whether or not it can remove an electron from an atom, and that is something to consider also when we think about danger, because if you damage an electron in an atom, now you've got an ion that will want to either grab a new electron or maybe do a different chemical reaction, or possibly it breaks a chemical bond because it's breaking an electron out of a bond pair. And so this is what we think about when it's a dangerous ability. So something that has a lot of ionizing ability can do a lot of damage to us. Alright, so let's delve into them. Alpha particles are our first one on the list here. Now, an alpha particle is 2 protons and 2 neutrons, which makes it a helium nucleus. Okay? It is chemically identical to a helium nucleus, and in fact, if you have an alpha emission, after a few seconds it slows down enough because it's collided through the air, and it turns into helium gas, and you can produce helium gas this way. The AZE notation for helium is 4-2. Note, the 2 down the bottom tells you how many protons something has. The 4 at the top tells you the total number of nucleons. So in this case, well, if there's 2 protons and the total is 4, we must have 2 neutrons. 2 plus 2 is 4. He for helium. Sometimes I've seen people write it with an alpha symbol, but the syllabus that we're using says He, so we'll stick with that. And we're also, in this year, we're going to look at this 2 plus here on the end, because this is just the nucleus. It doesn't have any charge, and so it's positive. There's no electrons to counter those 2 protons. It does have a total mass of roughly 4 atomic mass units. It's a little bit over, but you can look those things up. So there's our charge and there's our mass. They do have a very low penetrating power, because because of their mass and charge. They can't really get much through, say, for example, the skin on the outside of you, that is. But if you ingest it, it can be quite bad because the inside of us doesn't have this protection of a dead layer of skin, and their ionizing ability is very, very high because of both their mass and their charge. They're positive, so they're going to smack around other electrons pretty easily, and they're an entire atom nucleus, so they are very big compared to these electrons. So in terms of damage, it's very bad for you if you ingest it. Polonium-210 has been used as a poison for quite some time. The Russians seem to like using it. Let's move on to beta-negative particles. Now, beta-negative particles is what the simulation is called beta particles, because we're going to see that beta-negative and beta-positive has a lot of very similar properties to them. Now, all a beta-negative particle is an electron, so that means it has this notation. You can see here it has a nucleon count of 0. There is no protons or neutrons in the middle. It has an E for electron, and it's got a -1 to say that its charge is -1, or that it's got a -1 proton count. Realistically, we could do this as 0, 0, and then put a -1 up in the power to say the charge, but this is really useful for when we do nuclear reactions. So that's the way we write it, because it makes doing some of the math that you have to do in the next video very easy to deal with. So what makes this different from an electron? Its speed. It moves very, very, very fast. Apart from the speed, they are identical to electrons found in any other atom, so that means their mass and their charge, or the charge is -1 because it's an electron, and their mass is the same as 1 electron. So if you go back to the previous video where I have the mass of the 1 electron, or you check your textbook, you'll be able to get that out of there. And now this very high speed and their small mass means they can penetrate very easily into materials. They get through our skin, into the soft tissue underneath, so the penetration is actually reasonably high. But their smaller mass means that they can't ionize things too well because they're just electrons. So their ionization isn't as high as an alpha particle, but they can go further into you than an alpha particle. So their damage is pretty bad if it's ingested, and it's only slightly bad on the surface. It's not as great on the surface of your body, but it's, you know, something that you can deal with. The next one is beta positive, otherwise known as a positron, and this is an antimatter electron. Okay. This is the same AZE notation, 0 + 1 E, but instead of, note here we've got 0 for the nucleon count, so it has no protons and no neutrons, but it has a +1, and the reason that it's down there is because it makes the math easier, because it does have a positive charge. Now, I want to talk about antimatter quickly for a second. Antimatter is like an opposite form of regular matter that you and I are made up of. When matter and antimatter meet, they annihilate each other into energy. We'll look at that later on in the standard model. Why there is so little antimatter is one of the weird questions of the universe we haven't really answered. In fact, 1 gram of antimatter hydrogen is worth about $94 trillion US. So it's one of the most, well, I think it is the most expensive material on this planet. Okay. Because the notation is the same, that allows us to infer that the charge is the same but opposite, and the mass is also the same as 1 electron. Okay. Because of that, it means the penetration and the ionizing abilities are also the same, because the only difference here is the charge. And realistically, the only thing that, apart from causing an matter-antimatter annihilation if a positron hits an electron, which does release a little bit more energy, the damage is going to be pretty much the same. In fact, we use positron in something called PET scanning, positron emission topography, in order to look inside human bodies, which is a very useful ability of it. The big difference is that beta positive particles turn one way in a magnetic field and beta negative turns another way, but we will look at that in electromagnetism in Unit 4. So it is bad if ingested, and it's slightly bad on the outside. So far we've looked at 3 types of radiation, and they've all been particles. We've got them here on the left, our alpha particle, our beta minus, and our beta plus. But there are some well, these all have mass and high energy, and so they are ionizing. They can knock those electrons off. They either break free an electron or they damage a chemical bond. But there are some levels of light that can do this. So we've got gamma rays, we've got X-rays, and we've got UV rays. That's why you wear sunscreen when you're out. Visible light and low energy waves like microwaves can't do this. They don't have the energy. Of these three anyway, only gamma rays are considered nuclear in this case because they come from the nucleus. Some X-rays actually have more energy than gamma waves, and I'll show you a picture of this in a second, but they come from electron interaction, so we don't really deal with them in the unit. So whether something is an X-ray or a gamma ray depends on where it comes from. So we're just going to deal with gamma rays. So you can see X-rays are here, while gamma rays are here, and because this is the shorter wavelength, which means higher frequency, this region over here is the high energy. Cosmic, gamma, X-ray, ultraviolet. Cosmic is like stuff from the sun and stuff. While the stuff over here, after we get past visible light, is low energy. So radio waves, for example, we have millions of those going through us every day from local radio towers. We've got microwaves, and you've got infrared, which feels quite warm, but otherwise is reasonably low energy. Now, these two here are right next to each other, and originally we thought, yep, they were very distinct, and so it was about their energy, but nowadays we can produce X-rays from atoms that would be considered gamma rays in terms of energy, but because they come from electron interactions and not nuclear decay, they are called something else. So gamma rays, as you know it, have to come from a nucleus. That's something fairly important. So unlike the other three in our unit, gamma rays are not a particle. Now, I didn't animate this. This is the symbol we represent them in our equations. It's the Greek letter gamma, and it's kind of like a weird looking Y. I'll show you how I draw it. I'll just draw it as this when I'm writing, and that is perfectly fine. You will have something that looks approximate. If you want to draw a Y, I'm going to be able to figure it out. It's not a big deal. So, unlike the other three, this is a type of light. Okay? They will appear in the nuclear equations. Gamma rays often accompany other types of radiation, but you will get the occasional nuclear equation that just has gamma. Most of the ones you looked at in the simulation that we saw earlier on, you saw that most things that had gamma also had either alpha or beta. In fact, I'm not sure if any of those examples didn't have anything, actually had anything that just had gamma on it. So from what you've probably seen so far, they're always going to have either gamma with alpha or gamma with beta. Because they are made of light, they have no charge and they have no mass. But they also have exceptionally high penetrating power. Several inches of high density metal, such as lead, will stop them. Water, concrete. But because they're so good at going through atoms without colliding, that means their ionization ability is quite low because they don't really hit things. That being said, if you stand near a massive gamma source, you are going to get very, very sick very, very quickly, because even though each individual ray has a low chance, there would be a lot of rays coming from a gamma ray source. So even though we've looked at these three and said, oh yeah, alpha has a very low penetrating power, and it's not super damaging if it's on the outside. Well, beta is a little bit worse, and then gamma, is really bad, but because it goes right through you, but it doesn't have a great ionization level. If I was to get the same intensity of source and make it a very high source, well, alpha would burn the skin. Beta is going to be burning the muscle and the organs underneath, and that's going to cause some serious problems for you, while alpha particles burning your skin, it's a pretty nasty sunburn sort of level, but ultimately your skin is made to be damaged, while gamma rays would just end up killing you very, very quickly. While we would recommend their damage is just generally low on a single emission compared to alpha and beta. So if we had one single alpha particle, one single beta particle, and one single gamma ray, the gamma ray is probably not going to do much to me because it's just going to go right through me. The alpha is going to burn my skin, and the beta will just do some damage inside. If I gave you a lot of these things, the gamma rays are going to mess you up. Now, there's another subatomic particle mentioned in the text called a neutrino. We will use these a little bit when we do nuclear equations in the next video, but and we'll certainly look at them when we do the standard model very lately on, but they are not too relevant for right now. So just have a read over them quickly. Neutrinos and antineutrinos are emitted during beta radiation, so they always go with beta radiation, and they very weakly interact with matter. And what I mean by that is that they will just go right through you, and you won't even notice that they've gone through you. The last thing of note is the idea of shielding, and that is that different types of radiation require different types of shielding and thickness to stop them. The quality or the thickness of the shielding is related to the penetrating power. Alpha radiation can be stopped with clothing or the dead skin on your body. If you're a couple of centimeters away from it in air, that's fine. Beta radiation will go a couple meters in air, but if you use something like a book or some thin metal, you can be fine. Gamma radiation, though, will go over a kilometre through the air, and generally you need some thick, dense metal to protect yourself. So this image here is pretty good. We can see alpha's stopped pretty easily, beta next step, X-rays and gamma rays, because they're both light, stopped through lead and iron, which is why X-ray technicians wear lead aprons to help protect themselves when they are doing X-rays all day, and why when you go to get an X-ray you wear an apron over the bits that don't need to be X-rayed. But you can see a couple of other particles there. Neutrons will go right through lead because they're neutral and they don't react with the electromagnetic field around it, and they don't get bounced off by the nucleus because there's no positive proton repulsion. And so generally we need stuff like water or very thick concrete to stop a neutron. Neutrinos will go right through pretty much everything. Like a lot of the neutrinos going through you right now are going through the Earth first before going through you. So they don't really care about matter all that much. Okay. So that covers this video. So let's see, we've done three things. We have named our 4 types of radiation. We've gone through the properties of those different types of radiation, and we've looked at the shielding needed to block those radiation types. For your entrance slip, please go to the O-Book and download chapter 5.2. I have a read of 5.1, but I don't care about the questions too much. Download chapter 5.2, complete questions 1 to 6 in chapter 5.1. Question 6 is going to be a tricky one, so have some fun with that. And please put the answers into the 2.1.2 space on eLearn. Remember, this is from the Unit 1-2 textbook, and we are now dealing with the Unit 2 section on eLearn. Thanks for listening, guys. Have a good one.